49 years ago, humanity threw a metal probe into the dark and told it to keep going. Nobody expected it to still be talking to us today. But 1 minute ago, Voyager 1 sent back a signal that made engineers at the Jet Propulsion Laboratory stop what they were doing and stare at their screens in silence. 16 billion miles from Earth, in a region of space so empty that scientists once called it featureless, the oldest surviving spacecraft in human history has just handed us a puzzle nobody can solve. And the strangest part is that this is not the first time Voyager 1 has done this. It has been quietly rewriting the rules of physics for years, and almost nobody outside a small circle of astrophysicists has noticed. Voyager 1 launched on September 5th, 1977, riding a Titan Centaur rocket into a sky that still remembered the moon landings. Jimmy Carter was president. The first home computers were barely out of garages. Nobody on that launch pad could have imagined that the little spacecraft they were sending toward Jupiter and Saturn would still be transmitting data almost half a century later, from a distance so vast that light itself takes nearly a full day to make the trip. Voyager 1 finished its planetary tour decades ago, flying past Jupiter in 1979 and Saturn in 1980, capturing images that rewrote textbooks and revealing active volcanoes on the moon Io. Then it kept going, past the edge of the planets, past the reach of the solar wind, and in 2012 it crossed a boundary no human object had ever crossed before. It left the heliosphere, the vast bubble of charged particles blown outward by our sun, and became the first machine built on Earth to enter true interstellar space. That crossing should have been the end of the strange stories. Instead, it was the beginning. The moment Voyager 1 slipped into the space between stars, its instruments started returning numbers that did not match a single prediction. Scientists had modeled interstellar space for decades, using theory and indirect observation, confident they understood roughly what to expect. They were wrong. The plasma density Voyager measured on the other side of the heliopause was 40 times higher than anything predicted inside the bubble, a jump so extreme that some researchers initially suspected an instrument failure. It was not a failure. It was real. Interstellar space, it turned out, was denser, more turbulent, and far less empty than anyone had imagined. Then came the magnetic field problem. Every model of the heliosphere predicted that once Voyager crossed into interstellar space, the direction of the surrounding magnetic field would shift sharply, snapping into a new orientation dictated by the galaxy rather than the sun. Instead, the field barely moved. For years, this discrepancy sat unresolved, a nagging 4-decade-old mystery that suggested either the models were broken or Voyager was seeing something science had never accounted for. It took a team from the University of New Hampshire, combining data from Voyager with observations from NASA's Interstellar Boundary Explorer, to finally explain the anomaly, discovering that Voyager was still being tugged and distorted by the fading influence of our own sun's magnetic reach, bending the true interstellar field by more than 40 degrees from what other instruments recorded. Even after that explanation, researchers noted the field was still slowly rotating, still not behaving the way clean textbook physics said it should, and they predicted it would take another decade before Voyager finally reached a truly pristine, undisturbed patch of galactic space. If that were the whole story, it would already be one of the strangest tales in the history of exploration. But it is not the whole story. In 2017, something else appeared in Voyager's data that nobody had been looking for. Researchers going back through years of recordings from the spacecraft's plasma wave instrument, the tool designed to listen to the vibrations of charged particles drifting through space, found a faint narrow band of emission running continuously through the noise. It was not tied to any solar event. It was not triggered by a shock wave rippling out from the sun the way earlier plasma oscillations had been. It was just there, a persistent hum coming from deep in the emptiness, quietly present since at least 2017, and still detectable years later. Scientists nicknamed it the interstellar hum, and to this day, nobody has fully explained its source. The leading theories point to thermally excited oscillations in the ambient plasma, but the paper describing the discovery openly admits the mechanism could only be truly clarified by future missions, because Voyager, brilliant as it is, was never built with instruments capable of dissecting this kind of signal in detail. Then, in early 2025, the story took its strangest turn yet. Engineers monitoring the plasma wave system began noticing something unlike anything Voyager had ever returned before. Instead of the familiar low hum of interstellar plasma, the instrument began recording a sharp, rhythmic pulsing, an almost heartbeat-like pattern arriving at steady intervals from a region of space long assumed to be silent and uneventful. Teams of astrophysicists across multiple institutions pored over the readings, cross-checking instrument calibration, ruling out spacecraft malfunction, ruling out interference from Earth-based systems, and coming up empty. Some proposed Voyager might have drifted into a previously undetected plasma bubble, a localized density wave rippling through the interstellar medium. Others floated the possibility of a distant shock wave, the leftover energy of an ancient supernova finally washing over the tiny spacecraft billions of miles from home. Nobody has confirmed either explanation. The signal remains, technically speaking, unexplained. This is the point in the story where most videos would leap straight to aliens, and it is worth pausing to say clearly that mainstream scientists are not doing that. But it is also worth being honest that even serious researchers have acknowledged the eerie quality of what Voyager found. Because when your most careful physical models fail to explain a rhythmic signal arriving from empty space, the human brain cannot help but reach for the strangest possible explanation. NASA has not confirmed any exotic origin. What NASA has confirmed is that Voyager 1 keeps finding things nobody predicted, in a region of the universe humans have never directly sampled before, using instruments built with 1970s technology that nobody expected to still be working today. And this is exactly where the quantum angle enters the picture, because 2026 has quietly become the year quantum technology started reaching toward the stars. Just weeks ago, a coalition of quantum computing companies and research institutions announced the formation of America's Quantum Space Initiative, a partnership bringing together the neutral atom quantum computing firm Inflection, the aerospace and defense company Voyager Technologies, the quantum firm Monarch Quantum, the space infrastructure company Armada, and researchers at the University of Colorado Boulder. Their stated goal is to push quantum sensing, quantum computing, and quantum secure communication out of the laboratory and into real spacecraft, aiming to give future missions a level of precision and resilience that classical instruments simply cannot match. It is a striking coincidence that a company literally named Voyager is now at the center of humanity's push to bring quantum technology into orbit and beyond, even though it has no direct connection to the aging 1977 spacecraft still flying through the dark. But coincidence or not, the timing has captured public imagination, because the tools being developed under this initiative are exactly the kind of instruments that could one day help scientists finally decode signals like the ones the original Voyager 1 has been sending home. Quantum sensors work in a fundamentally different way than the classical instruments bolted onto Voyager nearly 50 years ago, where a traditional magnetometer or plasma detector measures a signal directly. A quantum sensor can exploit the extreme fragility of quantum states, using atoms cooled to near motionless stillness to detect impossibly tiny fluctuations in magnetic fields, gravity, and particle density. In theory, a quantum-sensitive instrument placed in the same region of interstellar space Voyager currently occupies could pick up structure in that mysterious pulsing signal that 1970s hardware was never built to resolve. It could distinguish between a density wave, a supernova remnant, and forms of interstellar turbulence nobody has even cataloged yet. That is the real promise behind pairing quantum technology with deep space exploration. Not proof of anything exotic, but the possibility of finally getting sharp enough eyes to read what Voyager has been trying to tell us for years. Consider just how remarkable it is that any of this data exists at all. Voyager 1 is powered by a radioisotope thermoelectric generator, a device that converts the heat of decaying plutonium into electricity, and that generator has been losing about 4 watts of power every single year since launch. Engineers have spent decades meticulously shutting down non-essential systems to preserve just enough power to keep the spacecraft's remaining instruments alive. By early 2026, only 2 science instruments were still functioning, the magnetometer and the plasma wave subsystem, the very tool responsible for capturing the mysterious pulsing signal in the first place. The cosmic ray subsystem was switched off in February 2025. The low-energy charged particle instrument followed in April 2026. Every remaining watt of power on Voyager 1 has been rationed with surgical precision, because the team at JPL knows that once the lights go out for good, there will be no way to send anyone else out there to check. Communicating with this spacecraft has become its own extraordinary challenge. As of today, a radio signal leaving Earth takes close to 23.5 hours to reach Voyager 1, and the reply takes just as long to come home, meaning a single question and answer exchange with humanity's most distant machine now eats up nearly 2 full days. On November 18, 2026, at 2:16 in the morning Pacific Time, Voyager 1 will cross a milestone no human-made object has ever reached before, becoming exactly 1 light day away from Earth, a staggering 16,094,000,000 miles into the void. At that point, sending a single command and waiting for confirmation it worked will take a full 48 hours round trip. Engineers describe it less like remote operation and more like slow-motion correspondence with a machine so far away that by the time it hears you, the version of Earth that sent the message barely exists anymore. And still, despite the failing power, despite the crumbling thrusters clogged from decades of use, despite operating with no backup systems left for almost anything on board, Voyager 1 keeps sending back readings that challenge what scientists thought they knew. Suzanne Dodd, the Voyager project manager at JPL, has described the spacecraft's current state bluntly, noting that everything left running on board is now single string, meaning there is no redundancy left if any part fails. Every signal Voyager 1 sends home today could, in theory, be its last. That fact alone has turned every strange reading, every unexplained pulse, every unpredicted density, spike into something closer to a message from a dying oracle than routine telemetry from a machine. Some scientists believe the interstellar hum and the 2025 pulsing signal may ultimately be connected. Two symptoms of the same underlying structure in the interstellar medium that current models simply have not caught up to yet. Others suspect Voyager 1 may be brushing against the outer edge of a turbulent region shaped by the collision between our solar system's magnetic bubble and the wider currents of the Milky Way, a boundary so complex that even decades of data have not been enough to map it cleanly. What almost everyone agrees on is that the interstellar medium is far stranger, far more structured, and far more dynamic than the simple empty void generations of scientists once imagined it to be. Voyager 1, a machine older than most of the people reading this, has become the accidental witness to a version of deep space that textbooks have not caught up with. It helps to remember just how alone Voyager 1 really is out there. Voyager 2, its twin, launched 16 days earlier but took a longer route through the solar system, eventually becoming the only spacecraft in history to fly close past all four giant planets, Jupiter, Saturn, Uranus, and Neptune. Voyager 2 reached interstellar space in 2018, 6 years behind its sibling, and today sits roughly 21 billion miles from Earth, currently taking about 19 hours for a signal to arrive. Both spacecraft carry the famous Golden Record, a phonograph disc loaded with images, sounds, music, and greetings in dozens of languages, assembled under the direction of astronomer Carl Sagan as a kind of time capsule aimed at any intelligence that might someday intercept it. For nearly 50 years, that record has drifted through space alongside instruments now returning readings nobody predicted. A strange pairing of a message, meant for someone else, and a mystery humanity itself has not solved. Where Voyager's onboard computer runs on memory measured in kilobytes, a fraction of what a modern calculator carries, the quantum sensors being developed for future missions rely on manipulating individual atoms cooled to within a hair's breadth of absolute zero. Inflection's neutral atom approach, the same core technology powering its quantum computing systems, is being adapted for space-based sensing applications that could measure gravitational and magnetic fields with a sensitivity classical hardware simply cannot reach. Under the newly formed America's Quantum Space Initiative, researchers plan to move these tools out of laboratory prototypes and into real orbital and deep space demonstrations, with early showcases planned around industry gatherings later this year. The ambition is not to replace missions like Voyager, but to build the next generation of eyes and ears capable of finally resolving mysteries that 50-year-old hardware can only hint at. It is worth being clear-eyed about what separates confirmed science from speculation in this story. The plasma density jump at the heliopause, the 40-degree magnetic field deviation, the persistent interstellar hum discovered in archived data, and the unexplained pulsing signal picked up in 2025. All of these are documented findings published or reported by working astrophysicists and NASA-affiliated researchers. What remains speculative is the leap from unexplained to unexplainable, a leap that responsible scientists have consistently declined to make. Every strange reading Voyager has produced so far has eventually been narrowed down to natural, if previously uncatalogued, physics, even when the explanation took years of painstaking analysis to arrive. That track record matters, because it means the smart money is still on nature holding the answer, even if that answer has not been found yet. Still, there's no denying the emotional pull of a machine this old, still catching the universe off guard. Voyager 1 has already outlived the careers of many of the original engineers who built it, and some of the scientists now analyzing its data were not even born when it launched in 1977. Each new anomaly forces a fresh generation of researchers to sit with the same humbling realization that gripped mission scientists back in 2012, that interstellar space is a genuinely unexplored frontier, and that no amount of modeling from the safety of Earth can fully prepare us for what a probe actually finds once it gets there. The unexplained pulsing signal may eventually join the list of solved mysteries alongside the plasma density jump and the magnetic field puzzle. Or it may linger for years, an open question waiting for instruments sensitive enough, perhaps genuinely quantum instruments, to finally catch up with what Voyager has already seen. If you are enjoying this journey through one of the strangest ongoing mysteries in modern science, do not forget to hit like and subscribe, because there is a lot more of the universe's unanswered questions still to come. There is something almost poetic about the timing of all this. Just as Voyager 1's own power reserves tick down toward an inevitable silence, a new generation of quantum-powered instruments is being born on Earth. Instruments explicitly designed to succeed where 1970s engineering eventually will not be able to keep up. NASA's own projections suggest Voyager's radioisotope generators may supply enough power to return basic engineering data until around 2036, but the window for receiving genuine scientific readings, the kind capable of catching another strange pulse or another unexpected density spike, is closing far faster than that. Every year, another instrument goes dark. Every year, the list of things Voyager can still tell us grows shorter. Whatever secrets remain in that mysterious pulsing signal, whatever finally explains the interstellar hum, there's a real possibility that Voyager 1 itself will run out of power before humanity finishes decoding what it already sent us. That is part of why the emergence of quantum space technology feels so significant right now. It is not that anyone credible is claiming a quantum computer has already solved Voyager's mystery, because that has not happened, and any video claiming otherwise is stretching the truth. What is true is that the tools capable of picking up where Voyager leaves off are finally starting to exist. Quantum sensing networks, if eventually deployed on future interstellar probes, could measure magnetic field fluctuations and plasma density with a level of precision that makes Voyager's 1970s instruments look almost primitive by comparison. They could, in principle, resolve exactly what kind of structure produced that rhythmic pulsing in 2025, whether it was a density wave, a distant shock, or some entirely new category of interstellar phenomenon nobody has named yet. For now, that remains a possibility rather than a completed discovery. And honest science communication has to sit with that uncertainty rather than manufacture a clean answer that does not yet exist. What makes Voyager 1's story so gripping is not that it definitively proves something supernatural or alien is out there. It is that a machine built before most of its own engineering team was born keeps finding cracks in models that some of the smartest people alive spent decades building. Every time researchers think they finally understand the boundary between our solar system and the galaxy beyond, Voyager sends back one more reading that forces everyone back to the drawing board. The plasma is denser than expected. The magnetic field refuses to behave. A persistent hum hangs in supposedly empty space. And now, a rhythmic pulse that nobody can fully explain continues to arrive, one transmission at a time, carried across 16 billion miles and nearly a full day of travel time, from a spacecraft that was never supposed to survive this long in the first place. Somewhere in Pasadena, a small team of engineers is still listening, still translating faint radio whispers into numbers on a screen, still trying to make sense of a universe that keeps refusing to fit inside the boxes built for it. Voyager 1 was never designed to answer questions about quantum technology or interstellar turbulence at this level of detail. It was built to photograph Jupiter's clouds and Saturn's rings, a mission that officially ended more than 4 decades ago. And yet, here it is, still working, still transmitting, still forcing humanity to admit how little we actually understand about the space between the stars. Whatever finally explains that strange pulsing signal, whether it turns out to be a mundane pocket of interstellar turbulence or something far stranger waiting to be confirmed, one thing is already certain. The oldest machine humanity ever sent into the dark is still teaching us more about the universe than almost anything we have built since. In the end, the real headline is not that a spacecraft turned toward some mythical quantum zone, because Voyager 1 has no such capability and no such destination exists on any star chart. The real headline is stranger and, in its own way, more exciting. A machine older than color television is still sending back readings that stump some of the best minds on the planet, from unexplained density jumps to a mysterious rhythmic pulse nobody has fully decoded. And for the first time in Voyager's long life, a new class of tools is finally emerging on Earth with the theoretical power to help answer questions this old spacecraft has been quietly asking for years. Whether or not those tools ever get a clean shot at solving the mystery before Voyager finally falls silent, one thing is already beyond dispute. Nearly 50 years after launch, humanity's most distant machine is still writing the story, one impossible signal at a time. If this kind of deep space mystery fascinates you as much as it fascinates us, make sure you subscribe and turn on notifications, because Voyager 1 is not finished surprising us yet, and neither are we.